Welcome to Patrick Talks Physics. Today's topic is all about projectile motion. A complicated topic that involves two-dimensional physics and kinematics. So let's take a look at how we can make it a little bit more understandable and simpler. One of my favorite strategies to always consider is how can we make something more understandable. And with projectile motion, we can start by always including reference frames. It's important to identify the positive and negative direction in your vertical axis as well as in your horizontal axis, and keep this consistent throughout the entire problem. I would also highly recommend creating a table for every projectile motion problem. If we keep track of all of our information in both dimensions separately, it makes everything easier to follow. Here, we identify the displacement, velocity, and acceleration in the x dimension, as well as the displacement, velocity, and acceleration in the y dimension. Here you'll also notice that time is at the bottom because time is independent of all dimensions. You really can't go wrong if you include a reference frame and one of these charts with every projectile motion question. But there's one other thing to consider, and that's these kinematic equations. These will be the tools that you will use to solve every problem. And let's keep in mind some of the necessary information when using kinematic equations, such as find 3. 3 is important because to find something like time, we need 1, 2, 3 other variables in order to identify which kinematic equation to use so as not to get overwhelmed with the problem. With all this in mind, I guess it's now time to take a look at actual projectile motion, which of course always starts with a parabola. Now this beautiful shape represents every type of projectile motion that we can consider, so let's take a look at all of them, beginning with horizontal motion. Here is where an object is going to displace just vertically downwards when it's launched horizontally from a cannon. Our second type would be if we have zero displacement. So our object is launched and lands at the exact same elevation, so our displacement here is 0. We also have the type where the object lands at a different elevation from where it took off, and this could either be above or below the initial launch position. So this would be a third type of projectile motion. All these different types of projectile motion are just simply represented by the parabola. It's important to know all the characteristics of this parabolic shape and to carefully consider what type of a problem we are looking at. So let's take a look at what happens in each dimension horizontally and vertically with projectile motion. First off, in the horizontal dimension, represented by the letter x, it's important to realize that there are no forces. Once the projectile has been launched, there is nothing affecting its motion in the x dimension. This means we have zero acceleration and our velocity is going to be constant. Now in the y dimension, things are definitely a little bit different. We have gravity affecting the motion of this projectile, always pulling it in a downwards direction. So the force of gravity pulling it down means we have an acceleration, 9.8 meters per second squared, and as a result, our velocity is constantly changing. Now we must carefully consider that what goes up must come down. So in order to change direction at the peak right here, we're going to have a velocity of 0 meters per second in the y dimension. So let's consider a problem, a relatively challenging one, where we have an object that let's say is leaving from a certain elevation, let's say at the top of a cliff, and landing at a different elevation, let's say a little bit lower down. What this results in is a change in displacement in the vertical dimension. Our sample problem reads, an object is launched at a 40-degree angle of elevation from the edge of a 60-meter high cliff. The launch velocity is 90 meters per second. How far away will the object land, and what is the total travel time? Now with a problem like this, I'm always a fan of finding ways that we could represent the information. So for this reason, I constructed a chart that nicely separates things into x and y dimensions, such as this one. A chart like this is convenient for separating the information from the x and the y dimensions. And when we start using our kinematic equations to solve, let's keep in mind that we always need to find 3. Find 3 variables in the x or the y dimension, and keep in mind that time is a connector between the two dimensions, and then solve for a remaining fourth. Now in all problems, if there's an angle involved before we even get started, we need to figure out what the initial x and y velocities are, based on the information given, which is 90 meters per second, and the fact that we are launching at a 40-degree angle. So in order to solve for the x and y components of the velocity, let's draw a vector to represent the initial launching of this projectile. This is the moment that it leaves the cannon. Here, we have an angle of 40 degrees, and we also have an initial launch velocity of 90 meters per second. Now, since this 90 meters per second is at an angle, we have to acknowledge that some of it is going towards a horizontal velocity, Vx, and some of it is going towards a vertical velocity, which we will call Vy. We're going to have to calculate both of these components using trigonometry. Here's the hypotenuse, longest side. Over here we have the opposite, and down here, the adjacent. So in order to calculate these components, let's first take a look at the adjacent side and the hypotenuse side, and realize that to find the x component of the velocity, we're going to use the cosine. So writing it out, we have 90 meters per second times the cos of 40 degrees. And this will give us an answer of 57.8 meters per second. Now for the y component, we're going to use the opposite side and the hypotenuse. This is going to use our sine function. So here, we're going to write it down as 90 meters per second times the sine of 40 degrees. And that's going to give us an answer of 68.9 meters per second upwards. Well, now that we know this, let's take a look at the question as a whole. Consider the parabola that we begin with. We don't have an entire parabola represented in this question. We are starting up high on a cliff, and our object is going to land below. So we can basically eliminate this portion, but this little diagram is going to help us to analyze what's going on in the question. Now let's bring out our trusty chart that we showed earlier. To fill this in, let's first consider the questions we have to answer. First question says, how far away will this object land? So let's put a question mark by our horizontal displacement. It also asks us to find the travel time. So for the time, we'll put a question mark there as well. Well, now within the question, we could fill in some more information. Our cliff is 60 meters high. So that's going to be our vertical displacement. This object is going to fall 60 meters down. So let's indicate that with an arrow for now. We also know from the question what the velocities are for our horizontal and vertical components. We solved for those earlier. For the initial horizontal component, well, that's going to be 57.8 meters per second. And it's just in the direction of travel, so let's say that's to the right. For our vertical initial velocity, that's going to be 68.9 meters per second. And it's being launched upwards, so we are indicating that with another arrow. Now for the acceleration row, they're actually quite easy to fill out. Horizontally, there is no acceleration, no other forces influencing the motion, so we'll put a 0 here. Vertically, we always have gravity, 9.8 meters per second squared, as an acceleration downwards, so we indicate that with yet another arrow. Well, this looks straightforward enough, but in the vertical dimension, we need to figure out a reference frame because we have upwards and downwards arrows. So, for the purpose of our problem, let's draw ourselves a reference frame and let's maybe indicate that upwards is going to be positive. It's arbitrary, doesn't really matter. Downwards, therefore, will be negative. And since horizontally we only have one direction of travel, let's indicate positive to the right. Now that this has been identified, we could go back to our problem and change some signs. To the right is positive, gravity is downwards, which is negative, and so is the vertical displacement, and upwards becomes positive for the vertical velocity. So we're now ready to solve the problem. But let's consider one last thing that is so important when it comes to kinematic equations, and that is to find 3. Once we have 3 pieces of information in one dimension, and that could include time, then we are ready to solve. Vertically, we have 3 pieces of information, so that means we can solve for the time. And here, also pay attention that we have initial velocities. Final velocities are irrelevant to this question right now. So when we pull out our trusty kinematic equation chart here, we go to an equation where final velocity is completely irrelevant. So here's the equation we're going to use to solve for time. So let's write that down. Let's keep in mind we're using data from the vertical dimension. So our vertical displacement is going to be equal to the initial velocity in the vertical dimension times time plus 1/2 the acceleration in the vertical dimension, which is gravity, times time squared. As we plug in the information, we're going to be very careful with the signs. So here our displacement is minus 60, which is equal to our positive 68.9, which is our velocity, times time, And then let's consider we also have half of gravity, which is downwards, which is going to be a minus 9.8 times time squared. Now sadly, with the t and the t squared, we're going to end up with a quadratic. So we're going to put everything onto one side. And let's start with gravity, because that's the t squared part. 1/2 of minus 9.8 gives us minus 4.9 t squared. Our next part is going to have the t with it. So let's write down our plus 68.9 t. And let's bring this minus 60 over to the other side, which is going to make it a plus 60. And that's equal to 0. And this is where we have our quadratic set up. We can use a variety of methods to calculate the time, but if we plug it into an app or use the quadratic equation, we're going to end up with two solutions here. The first answer is going to be plus 12.8 seconds. And our second solution is going to be minus 0.96 seconds. Two answers, huh? Well, we have to ask ourselves, why do we always have two answers when we solve for this using a quadratic? Going back to our original parabola diagram, we'll notice that every elevation intersects the parabola at 2 points, and this is why we have 2 times. So let's consider our question, where we have a cannon launching an object that's going to land at a lower elevation. Well, there are 2 moments in time when we're at this lower elevation. One is going to be the positive number that we came up with, and another one is actually before the moment of launch. So that's why we end up with a negative number for the second example. This fact helps to clarify which of those 2 times we need to consider. And for the purpose of our question, we can now cross out the negative time and circle the 12.8 seconds. So that's what we can enter onto our chart. Since time beautifully connects the 2 dimensions, we can now consider the fact that we have 3 pieces of information in the x dimension, so we should have enough information to solve for the last part of our question, which is the horizontal displacement. Well, it's once again time to take out our trusty equation sheet and figure out which equation is going to be the most helpful for solving for our horizontal displacement. If we look at the data that we have the time, the acceleration, and the initial velocity, and we want to find the displacement. Final velocity, once again, is not going to be helpful, so we're going to use the exact same equation. But we're going to notice that this time it's going to be a little bit easier. If we write down our information for this equation using horizontal data, our horizontal displacement equals our initial horizontal velocity times time, plus half of our horizontal acceleration times time squared. Recall that the acceleration is 0, so this whole part of the equation cancels right out. So let's take our velocity of 57.8 meters per second, and we're going to multiply that by the time we've already calculated, which is 12.8 seconds. When we multiply this out, we end up with the final answer for our horizontal displacement of 881 meters. Last thing to consider are the significant figures within the question. Here we have 3 and 3, so 881 is a perfectly acceptable final answer. And there you have it, some useful tools to help solve projectile motion problems. Projectile motion always comes down to a parabola. Analyzing the details of this parabola will help us solve what we need to know. Keep in mind, when using kinematic equations, we're always going to have to find 3 in order to solve for a 4th variable. Some other things that we considered is organizing our information in a convenient chart, like this one where we separate the 2 dimensions. We also keep in mind our reference frames, and we should have all the tools we need to solve every projectile motion question. Thanks as always for listening. Until next time.